Now let's relate our derivation to the moment. Try to express the moment m in terms of axial stress sigma and position for neutral axis y. Consider a differential area dA which has an axial stress sigma. It is located at position y from the neutral plane. The differential moment generated by this differential area is given by dm equals to y times sigma times dA. Notice that there is also a negative sign because in case y is positive, then it will generate a negative moment. That is, for this differential area element located at position y, if the sigma is positive, then it is a force like this. But we know for this moment, it is actually negative as what we defined previously. That is, we must put a negative sign in front of it. Since we know that sigma equals to E epsilon equals to minus EY divided by rho, then we substitute the stuff into it to get dm equals to E divided by rho times y squared dA. We integrate both sides to get m equals to E divided by rho, since they are constants, times to the integral of y squared dA. As we introduced in tutorial 0, it is just the second moment of inertia with respect to z-axis. However, in the later examples of this tutorial, I will write it in Ixx because it is rather convenient to set this axis to be x, then we set the longitudinal direction to be z-axis. So bear in mind with that. So although here we say it is the second moment of inertia in z-axis, but later when I deal with the problems, I will adopt this axis to be x. Okay. So it is up to you whether to adopt z or x, but all in all, you just need to understand the underlying principles or the reason why you should do that, then it is okay no matter which notation you use. Now combine those results, we have m equals to EI divided by rho, but we know that we can express E in terms of sigma x divided by epsilon x, and the epsilon can be further expressed in minus y divided by rho. Then you can get this equation. Notice that it is very hard to get rho in practical applications, so we seldom take it into consideration. So we want to eliminate it by using other means. This is why we substitute E equals to this and epsilon x equals to this to get an alternative result. Finally, we rewrite the equation to get the flexure formula, which is given by sigma x equals to negative of my divided by I. Before using this equation, please check that the cross-section is axially symmetric and the loading is 1D. In general case, the axial stress inside the bar over 2D and the asymmetric cross-section is given by this formula. It was taught in Macan 3650 aircraft structures. As you can see, if the cross-section is not axially symmetric, then Ixy is non-zero, then the whole expression will be rather complicated. Therefore, we require the cross-section to be axially symmetric. Actually, we can simplify this very complicated equation by using our assumptions before. First, given that it is 1D loading, that is, my equals to 0, but you know this piece equals to 0 means that the whole piece equals to 0. Besides, Ixy equals to 0, that means this is 0, this is 0. Finally, you cancel out Iyy, then you will have only minus mxy divided by Ixx remaining. So this is why the two assumptions are so important.